Welcome to the lecture on the real number system. Today we're going to talk about all the different real numbers and what categories they lie in. And we're going to start with the natural numbers. The natural numbers are just your counting numbers. And these are 1, 2, 3, 4, 5, etc. going on up. The next largest set of numbers is the whole numbers. The whole numbers contain all of the natural numbers. The only thing we've done is we've added 0. So 0, 1, 2, 3, 4, 5, and so on. What's missing now are the negatives. So the integers is the next largest set of numbers, and it contains all the positives, all the negatives, and 0. The next largest set of numbers are the rational numbers. The rational numbers can be defined a couple of different ways, and the formal definition that I'm going to give you is that any rational number is a number that can be written in the form p over q, where p and q are integers, and we're also going to stipulate that q can't ever equal to 0 because we never want to divide by 0. So basically a rational number is anything that can be written as a fraction. Now there's an alternative definition that we sometimes talk about dealing with decimals. When you talk about rational numbers, we can also say that any rational number should be a decimal that terminates. Terminates means that it needs to end or stop, or it could be any decimal that repeats. So let me give you some examples of some rational numbers. -3 is a rational number because it's an integer, and all integers are also rational numbers because they can be made into fractions by just putting them over 1. 0 is also rational. 1.5 would be an example of a rational number because that would be an example of a decimal that terminates or ends. For the same reason, 0.25 would also be a rational number. 0.25 is also rational because we know that as the common fraction 1/4. So any number that can be written as a fraction is also rational. Some other examples would be 0.3 repeating. 0.3 repeating repeats, so it fits our informal definition. It's also the same as the fraction 1/3. Some other examples, mixed fractions like 1 7/8, or even improper fractions, -13/5, would all be examples of rational numbers. The next set of numbers that we're going to talk about are just the opposite of your rationals, and these are called your irrational numbers. Irrationals are all numbers that are not rational. So if we refer to our informal definition, that refers to the fact that you're looking for decimals that do not terminate, so they should never end, and at the same time they should not repeat. So these would be decimals that go on forever with no specific pattern. The most famous irrational number would be pi, 3.141579 ... That goes on forever. Another very common irrational number that has its own special symbol would be the letter e. E is the decimal 2.71828, and then it continues on forever. We use this quite often when we talk about logarithms and exponents. Some other irrational numbers would be things like the square root of 2, square root of 3, square root of 5, square root of 7, or the square root of any prime number. Okay? Now when we put all these different categories of numbers together, what you basically create is your real number system. So I'm going to draw a Venn diagram, a circle diagram, to kind of show how everything is related to one another. Now our smallest set of numbers were the natural numbers, those counting numbers, 1, 2, 3, 4, 5. The next biggest set of numbers are your whole numbers, which contain all the naturals, but then you've added in 0. The next biggest set of numbers are your integers, which just adds in all those negative numbers. Then your next biggest set of numbers are the rationals, all those fractions and decimals that repeat or terminate. The irrationals are the exact opposite of your rationals. So the irrationals are going to be their own little circle. There should be no intersection or overlap between the rationals and the irrationals, because you're either one or the other. And then the real numbers contain all of those. So here's our relationship. Now, in introductory algebra, we really just talk about the real number system, but when you move on to intermediate algebra, we sort of make that set a little bit larger by talking about something called the complex number system. Why do we need complex numbers? Well, there's some limitations to real numbers. If you remember that when we talk about square roots, we are never allowed to take the square root of a negative number. We know that square root of positive 4 equals to 2, but square root of negative 4 doesn't exist because there's no number that you could square that's going to give you negative 4. Nothing squared will ever equal negative 4. Positive 2 squared is positive 4. Negative 2 squared, because you square the negative, would also be positive 4. So there's no real number that's going to allow you to have a negative under the square root. So what the complex number system does is it creates this imaginary number I, where I is strictly defined to be the square root of negative 1. Therefore, if you have the square root of negative 4 that you're looking for, we can break this up to the square root of 4 times the square root of negative 1. Square root of 4 becomes 2, and square root of negative 1 becomes I. So square root of negative 4 becomes 2I. So the complex number system includes more numbers than the real number system because it's going to include these numbers that have an I in them, and sometimes we write that as A plus BI, where A and B can be any real numbers at all. Some examples of complex numbers would be things like 2 plus 3I, 4I minus a half, 1/3 I, or negative 5I. These two examples on the end contain only the i's and there's no constant a in front of them. So these are called pure imaginary numbers. So if we go back to our Venn diagram from above, let's add in these complex numbers. The complex numbers are going to be all the reals, and in addition, these new numbers of the form A plus BI, where B doesn't equal 0, so there has to be an I term in there. As a subset of those, you could have things of the form BI, which we call our pure imaginary numbers. So you have your things with i's over here, you have all your real numbers over here, put the two sets together, and you create your complex number system. That concludes our lecture on the real number system. Good luck.